Hi everyone, I'm Ziming, a computer science major sophomore at NYU Shanghai. This semester I took a really enlightening and challenging course called Machine Learning and Data Mining led by Professor Keith Rose. Today, I'm really excited to present you what I did for my final project using those machine learning algorithms. Some of my slides are adapted from Professor Rose, which he may also adapted from other professors listed below. My project is about flag classification. The motivation about this project came out of my mind when I recalled that when I was a boy, I had a hard time distinguishing national flags that are similar. Even now, I still cannot tell the difference between Chad and Romania. Therefore, after I took this course, I thought it was an amazing idea to use machine learning to solve my problem. Today, I'm going to use a cool algorithm called support vector machine, short as SVM. SVM is something I think is visually straightforward but very hard implementing. Let's first see how it works. The very basic idea of SVM is to find a plane factorized by a mathematical expression with feature vector x. Together with the weight vector omega, this expression throws out an output indicating the class of the input vector. As it was shown on the graph, we can get the first key ideas of SVM, which is to use optimization to find solution with the largest margin. However, it is not always the case to find a possible solution. For example, the data points may not be linear separable. Thus, we follow the second key idea, which is to seek large margin separator while allowing for some test errors. But we cannot sacrifice our model's accuracy all the way to achieve larger margin. Hence, we still need nonlinear models to make this algorithm applicable for more general datasets. However, the new model also brings new problems, which is the huge amount of computations, which is even intractable for a supercomputer. Thus, to reduce complexity, we use a new vector to map with original nonlinear terms such as exponentials and so on. Then the equation is back to a linear one. This is also known as the third key idea of SVM, which is called the kernel trick. Though the computation work is reduced sharply, it still involves some complex mathematical transformations to get to the final optimization equation for the computer to compute. Okay, so now we had a big picture about the algorithm lying behind this machine learning method, and we can start building our programs. 12 similar flags were selected out of total 196 countries and labeled from 1 to 12. For each country, I selected 15 different flag images. For simplicity, here I used the pure flag images pre-processed by me. In the image, information other than the flag itself are cropped and discarded. Therefore, those images are kind of same in scale and size now. However, they're still in different brightness level and wavy shape, as you can see. So how can we solve the illumination condition challenge? As a programmer, you definitely don't want your program dies at the infant stage. Therefore, we use the magic formula which calculates the proportion RGB takes within a single pixel and then restore it by multiplying 255. This shrinks the brightness deviation between images greatly. Since we restricted the image size at 52 by 32, so now we have our data dimension of 52 by 32 by 3 of each one of 15 images of each one of the 12 countries. Then we write them to CSV files for the convenience of manipulations using R. In R, we first load data, then merge them into a training set of 120 images and a validation set of 60 images. For the tuning part, I was using 30 different gamma values and 3 different cost values to try to capture the best parameters. So now let your program run. Now let's check the result of our first attempt. As we can see, in general the result was pretty good, but for the first 4 classes, it did a very bad job, which is the part I care about most. Therefore, we can enhance our model by adding more training sets to these classes and also give more freedom to parameters when tuning. Here we check the result again and we find that the prediction for the first 4 classes indeed improved a lot, which gave almost a 5% of accuracy boost in total. Also, the diagram shown on the upper right kept tracking the error along with the change of gamma, indicating a relatively low error for small gamma values. I believe that if I keep adding images to my training set and try out more values, I would be able to find an even better result. So basically that's it. Please feel free to throw me comments and thoughts. Thanks for watching.